Hello everyone, my name is Emma Davidson and today I'm going to be talking to you about the mechanism of nucleophilic acyl substitution. Nucleophilic acyl substitution is a very versatile mechanism, which is why it's important to be familiar with. I have an overview of the mechanism up here, and then some of the compounds involved in the reactions that it's in down here. So some of these reactions include the Fischer esterification reaction, conversion between derivatives of carboxylic acids, trans-esterification, and the Claisen condensation. Now that we have some background of where this mechanism is used, let's get into what's really going on in the mechanism itself. So generally, the two important compounds involved in this reaction are the carbonyl compound and the nucleophile. Somehow, through this mechanism, we get the end product in which the nucleophile, which we originally have reacting, replaces what was once attached to the carbonyl group. So to define some of those terms, first, the carbonyl is just a carbon atom that is double bonded to an oxygen. Typically, this carbon is bonded to two other things. The oxygen isn't bonded to anything else. So we'll come back and talk about some of its properties in just a moment. But onto that nucleophile. So a nucleophile is an electron-rich compound. This is a compound that donates an electron pair in a reaction and is typically negatively charged, has a lone pair of electrons to react with that electrophile. An electrophile is pretty much the opposite of a nucleophile. It is electron poor and will receive the electron pair in a reaction. So some examples of a strong nucleophile would be the methoxide ion. So it's negatively charged. It has this electron pair here that can react with an electrophile. An example of a strong electrophile would be a carbocation. So say this carbon atom here in this chain only has one hydrogen bonded to it, making it electron deficient, so it primes it for attack from this nucleophile. To remember these two molecule types, we can just look at their names. So phile means lover of. The nucleophile loves positive. Nucleus has the positive part of an atom, whereas the electrophile loves those electrons. It's ready to gain that electron pair. Going back to that reaction, we have our carbonyl compound in some sort of nucleophile. Now, this carbonyl is special because it has some resonance properties where this pair of pi bond electrons can shift up to this oxygen and form a resonance structure that might look like this. So now this oxygen has a negative charge and the carbon has a positive charge. So in reality, we typically draw it like this with the double bond, but this carbon really has a positive partial charge where the oxygen has a negative partial charge, and this is due to the high electronegativity of the oxygen and that resonance ability. So this primes that carbon atom for attack from that nucleophile, which is exactly what we see happening in this mechanism. We have a strong nucleophile with that electron pair that bonds to this carbon atom that has that positive partial charge, and that pi bond shifts its electrons up to the oxygen, and we get this tetrahedral intermediate because the carbon is bonded to 4 different things here. To form the final product, that electron pair on our oxygen will come back down and regenerate that carbonyl bond. As this happens, the original substituent of that carbonyl carbon is forced off, and we have only this nucleophile that just attacked remaining. So some important things to keep in mind if you're going to use this mechanism is you have to make sure that the group you intend to be leaving, in this case this X, is a better leaving group than that nucleophile. So a better leaving group is a weaker base or a less strong nucleophile, because the stronger nucleophile will maintain its bond with that carbon. So weak bases are typically the conjugate base of a strong acid. So one that's a good example would be the chloride ion, because it is the conjugate base of HCl, a strong acid. So here's just an overview of this generally written mechanism that we just went through. Again, we have our carbonyl compound that's reacting with a nucleophile. You undergo this nucleophilic attack to make this tetrahedral intermediate here, and you regenerate that carbonyl to form your new product with that nucleophile attached. Now that we have a basic outline of what's going on, let's see a real example. So in this case, we're going to complete a conversion between derivatives of a carboxylic acid. In this case, we're going to use this acid chloride, because we see we have this chloride attached to our carbonyl carbon with methoxide as our nucleophile. So methoxide is a strong nucleophile, so it attacks this carbon. Again, we have that positive partial charge because of the resonance ability of this carbonyl, which makes this possible, and we get this tetrahedral intermediate here. And to form that final product, our carbonyl is regenerated and the chloride ion leaves. The chloride ion is the conjugate base of HCl, which is a strong acid, whereas if we look at the conjugate base of the methoxide ion, it's methanol, which is not a strong acid. So in this case, the chloride ion is the one that leaves to form our final product in this reaction, where we now have an ester and we started with an acid chloride. We can see that here, start with an acid chloride to this tetrahedral intermediate to get this ester as our final product. Another example of this could be the Fischer esterification, where we have this mechanism at play. What's a little different about this is the carbonyl has to be protonated first, and this is because our nucleophile here is not a strong nucleophile. It's not deprotonated here. So in this reaction, you have an alcohol that reacts with a carboxylic acid to make an ester as your final product. Again, this is Fischer esterification, and it's acid catalyzed. So we see this source of a proton here, and we activate that carbonyl, making it positively charged here, which makes the resonance ability of this carbonyl come out, because once those pi electrons shift up, you no longer have a charge here. So we have our tetrahedral intermediate that forms. We deprotonate here using the same conjugate here of our acid or proton source. So essentially, this is the first step that's an acid catalyzed addition. The next step is an acid catalyzed dehydration, where we protonate here to get a water molecule that then leaves. And again, we just deprotonate up here that we protonated at first to activate that carbonyl to get our final product of an ester here. To conclude, some main points from this mechanism. You start and end with a carbonyl. What's different is one of the adjacent groups attached to that carbonyl. Carbonyl carbons have this positive partial charge. They're electrophilic, which is what makes them susceptible to attack from that nucleophile. If you're using this reaction, you have to make sure that your nucleophile is a stronger base than what you want to be leaving that carbonyl carbon. And finally, this mechanism is very versatile, and it can be used in a bunch of different reactions. That's it today. Thanks for listening.